This video is based on the application of particle swarm optimization algorithm for optimal placement of wind turbines in the wind farm. Step by step, we will try to understand this application. First, we will try to understand the optimization process objective, that is, why we need optimal placement for the wind turbines in the wind farm. Next, we will try to understand few facts about wind turbine, wind farm, wind speed calculation models, wind farm layout, and different scenarios for optimal position of wind turbines in the wind farm, different types of meta-heuristics that are used to solve wind energy optimization problems. In the end, step by step, we will try to understand how we can use particle swarm optimization algorithm to find out the optimal position for the wind turbines in the wind farm and its flowchart. So step by step, we will try to understand this whole process. First, we will start with the basic fundamentals so that we can easily understand how this is working. First, we will try to understand our objective, that is, why we need the optimal position for the wind turbines in the wind farm. Here you can see we have different key elements that play a major role in the wind energy projects. First, we have the investment cost. Investment cost is the total investment cost in the wind farm for wind energy project. Next, we have wind turbine cost. Wind turbine cost include wind turbine manufacturing cost, wind turbines transportation cost, and wind turbines installation cost. And here, wind turbine installation cost include rotor, blades, and gearbox installation cost for each wind turbine. And next, you can see the wind farm maintenance cost, construction cost, and the electricity production cost. And last one, we have the wind turbine lifetime that is affected by the wind speed. So we have the different key elements for the wind energy projects. Now we will try to understand the objective for the wind energy projects. So first objective, we have how we can minimize the total cost per unit. Next one, this is the prime objective, how we can produce maximum power energy at lowest unit cost. So here we want to minimize the cost, that is the total cost per unit. We want to minimize the cost, and here we want to maximize the energy production, that is the power production. So they are the two key objectives, how we can minimize the cost and maximize the power output. Next objective, we have noise minimization, that is how we can minimize the wind turbine noise in the wind farm. And the last one, that is the very important objective that affects the overall performance of the wind farm, that is how we can minimize the wake effect. So here we discuss different objectives, that is how we can minimize the total cost per unit, maximize the total power output, minimize noise, and how we can minimize the wake effect. So here we discuss different objectives and key elements for wind energy projects. So this is the basic diagram for the wind turbine. It includes tower, blades, rotor, gearbox, and generator. So here wind turbine is acting as a device to convert the wind energy into electrical energy, and in this process wind is used to produce electricity. Here the kinetic energy in the air is converted into electricity. And here you can see this is the power output generated by wind turbine. So you can see this is the power extracted by wind turbine. Here this is the power coefficient, and this one is the air intensity, and here this is the rotor swept area, and this is the wind speed. So this is the power extracted by wind turbine. So here you can see this is the wind farm, and it is also known as wind park or wind power plant. Wind farm include number of wind turbines in the same location used for energy production. If the wind farm layout is not properly optimized, it results in decreased power output and increase maintenance cost. So if the layout is not properly optimized, it increases the maintenance cost and decrease the output power production. So here you can see we have the wind farm, and we are using the wind farm for the energy production. Wind farm output power is affected by the wake effect. Wake effect reduces wind speed and it generates the turbulence in the wind turbine. A wake is formed behind the wind turbine, which affect the performance of downstream turbine. When free stream wind encounter the wind turbine blades, its speed decreases and turbulence intensity increases from a wake. In the objective you can see here we want to minimize the wake effect because it reduces the wind speed and it also generates the turbulence in the wind turbine. So here you can see we have the wake effect model. We can use wake effect models to estimate the power loss. Different wake models are used to estimate the power loss. Jensen wake effect model is one of the most popular analytical wake model. So here you can see this is the Jensen wake effect model. Here you can see we have wind turbine, and this is the distance between the wind turbines, and here this is the rotor radius, and here you can see this is the wake boundary, and here this is the wake radius, and this is the downstream wind speed, and here you can see this is the position for the wind turbine xy, and we can calculate the wind speed in the wake region for the ith wind turbine using this equation. So here you can see this is the drag coefficient, and here this is the downstream rotor radius, and here this is the constant, and this is the wind velocity in the wake region, that is the wind speed in the wake region for the ith turbine, and this is the resultant velocity when many full wake effect acting on the wind turbine. So we can use this equation to calculate the resultant velocity. So here you can see we have parameters and the parameter values that we can use in the wake model calculation. Here the rotor diameter is 40 meter, hub height 60 meter, air density, temperature 25 degrees Celsius, and wind speed is 12, and you can see the other parameters that is used in the wake effect model calculation. Next you can see here the wind farm layout design. Suppose we have wind farm area that is 2 by 2 kilometer, and this is the square field for planting wind turbines. Suppose we have a number of wind turbines. Our objective is to minimize the overall cost per unit and maximize the power output, and we also want to minimize the wake effect. So here you can see we have number of wind turbines in the wind farm. For the better results we will set the distance, that is the minimum distance between the wind turbines for the better results. So we will consider the minimum distance between two wind turbine, 5 times the rotor diameter. Minimum distance between two wind turbine is equal to the 5 times rotor diameter, and rotor diameter is 40. So here the minimum distance that we will consider between two wind turbine is 5 times rotor diameter. So here we have 40 into 5, that is 200 meter. This is the minimum distance we will consider between two wind turbines. Next, you can see here this layout area is divided into 10 by 10 grids, and here as the area is divided into 10 by 10 grid, it means we have 100 possible position for the wind turbines. For example, you can see here wind turbine, and we will denote its position with X and Y. So we have 100 position for the wind turbines in this area where we can plant different wind turbines. So now we have the area and we want to place the wind turbines, and the minimum distance is considered 200 meter between each wind turbine. Now we will try to find out the optimal position for the wind turbines, how we can place wind turbines. So we will try to find out the optimal position for the wind turbines using particle swarm optimization algorithm. For the optimal positioning of the wind turbines, you can see we have different scenarios. In the first scenario we have fixed wind direction. So wind direction is fixed and we have the constant speed, that is 12. Next scenario we have the variable wind directions and we have the constant wind speed. So we have different wind directions and wind speed is constant. For the third scenario we have variable wind directions and variable wind speed. So we have the variable wind speed, that is 17, 12, 8, and we have the variable wind directions, and the highest wind speed directions are considered from 270 degree to 350 degree. So we have different scenarios that are considered when we are trying to find out the optimal position for the wind turbines, because in the wind farm we have different scenarios for the wind turbines. So in the wind farm we have different cases for the wind turbines. For example, we have the first scenario where wind speed is constant and the wind direction is also constant. In the second scenario, wind speed is constant, but we have different wind directions. In the third scenario we have variable wind speed plus variable wind directions. So different cases affect the overall performance. Of the wind farm power production. Now you can see here we have different Meta-heuristic optimization algorithms used to optimize the wind farm layout and to find out the optimal position for the wind turbines in the wind farm. For example, PSO algorithm, ant colony, artificial bee colony, sparrow search, crow search, whale optimization algorithm, water cycle optimization algorithm, teaching learning based optimization algorithm, invasive weed optimization algorithm, genetic algorithm, and many more Meta-heuristic algorithms are used for optimization in the wind energy projects. Here we will use the particle swarm optimization algorithm to find out the optimal position of the wind turbines in the wind farm. So first we will initialize the algorithm parameters for this application. So first we have the population size, that is the total number of wind turbines in the wind farm is the population size. Lower bound and upper bound is considered as the wind farm boundary, as we cannot place the wind turbines outside wind farm layout. So this is the wind farm boundary. And we have the design variables like wind turbine parameters as you can see here, and the objective function, that is the cost function, problem constraints, current iteration, maximum iterations. Next we will initialize the optimization algorithm parameters. So here we are using the particle swarm optimization algorithm that we already discussed in this video. So for more details you can check this video. Here we will discuss the working according to this application. So for this algorithm we will initialize the parameters. Next you can see here we will initialize the population for n wind turbines in the search space. So here we have 30 wind turbines. So x1 is the position for the first wind turbine, x2 is the position for the second wind turbine, and so on. After that we will use the cost function to calculate the cost value, or we can say the objective function value for each wind turbine. So here we are using the objective function for minimization. So here we are trying to optimize the overall cost per unit, that is the cost function divided by total power output. So here we have the minimization function that is used as the objective function to calculate the cost per unit. So this is the cost, that is the combined power generated by n turbines, and this is the cost function. So here n is the number of wind turbines, and this function is calculated as combined power generated by all wind turbines divided by total power output of the wind farm. So this is the objective function used here to find out the fitness value for each wind turbine, and the wind turbine having the minimum fitness value is considered as the best. So here you can see the cost function, that is the total cost of wind turbines within the wind farm is calculated using this function, and when large number of wind turbines are purchased the maximum cost reduction is 1/3, and here this is the cost function. Next we have the total power calculation. So total output from ith turbine is computed using this. In the previous slide we discussed different scenarios where we have constant wind speed, variable wind direction plus variable wind speed. So here you can see we have limit from 0 to 360 degree. So we have different direction from 0 to 360. So this denotes the wind probability for a wind speed from specific direction. Next you can see here this one is the actual power output from ith turbine as a function of wind speed. So here this is our objective function, that is cost function, this one divided by total power output. Next we will check the counter whether the current iteration is greater than maximum iteration or not. If this condition is true we will move to the next step, else we will stop and display the best solution. After that we will update the agent's position, and here in the PSO we will update the velocity for each agent, and using this equation we can calculate the velocity and the position for each particle or for each turbine in the search space. After that again we will increment the counter. Now counter is 2, and we will check whether it is greater than maximum iteration or not. When the stopping criteria is met they will display the optimal solution, that is the optimal location for the wind turbines and the objective cost. Here, this is the flow chart. First, you will initialize the important parameters for this application and algorithm. After that, initialize the population for the n turbines. Then, using cost function, we will evaluate the population, and here we will calculate the fitness value for each. After that, we will check this if the stopping criteria is met or not. If stopping criteria is met, we will stop and display the optimal location for the wind turbines and the cost value. If stopping criteria is not met, we will update agent's position, velocity, and then again we will increment the counter, and here again we will calculate the fitness values for agents. Here you can see we updated agents, and here we will calculate the fitness values for each agent using the objective function, and again we will check the stopping criteria. If it is met, then stop, else again we will repeat this loop until the stopping criteria is met. And once the stopping criteria is met, we will stop and display the best solution that we find out in the previous iteration. So that's all about this video. If you have any questions, you can comment below, and thanks for watching this video.